Okay, so welcome everyone. So today it's my pleasure to welcome Gabriel Santin, who will be talking about hands-on introduction to graph deep learning with examples in PyTorch Geometric. So this is like 1/4 series, a tutorial series that will be every Thursday this November. And yeah, so that's it. Yeah, thank you, Gabriel. Thank you.
So thank you, Boumediene, for the nice invitation. Now is a long time since I'm attending this seminar, and it's really a pleasure to be able to give a contribution here. So as Boumediene mentioned, this is the first of 4 sessions that we will have. And the idea is to provide a practical introduction to deep learning on graphs, okay? And we will try to motivate the interest for this kind of techniques. So they are very somehow recent techniques and in machine learning, and they are starting also to be used in computational sciences and dynamical systems. And we believe that there will be a very large possibility for employment of these techniques in the field of dynamical systems, in the learning of dynamical systems. So before starting, I would like to comment on this list of seminar. So it's divided in 4 parts, and each of them is presented by one of the 4 of us. So I'm the first person here, and I'm working at the University of Venice, and the other 3 guys are working in Trento, still in Italy, at the University of Trento and at the Fondazione Bruno Kessler in Trento, where I was before moving to Venice. So each of these sessions will be presented by one of us, and you can find here the emails of each of us. So in the case you have questions, we will be very happy to try to answer them. And also we have our web pages, of course, where you will find material related to these slides and any other information. Okay. Roughly speaking, the outline and the organization of these sessions is in these 4 parts. So first, I would like to mention that we are not done yet, but we will be until next Thursday. We will have a small web page where you can find the slides of the presentation, and also not this session, but the other 3 will also have a practical part with some code, and we plan to publish also the notebooks related to some of the experiment that we are going to show. Okay, so the idea is really that if some of you is interested in using these techniques in their own application, it will be possible to at least start from what we are providing here. Okay, and so the 4 sessions are organized as follows. The first one today is presented by me, and the goal is to give some motivation on the modeling and the use of machine learning techniques on graphs, and some introduction to basic concept. And then I will give a definition of the computational structure of a graph neural network, and why do we need some particular neural network when working with graphs? So why can't we just use what is available for vectors, for example? Then the second session will be next Thursday and will be presented by Antonio Longa, and will be about more practical details of implementation. So how to translate what I'm going to present today into actual code, and in particular, we will do that in PyTorch Geometric. Okay, so by the end of this second session, you should be able to load your own dataset, your graph dataset, and to perform some classification or regression task on your graph. Then the 3rd and the 4th part, which will be in the next 2 weeks, will be presented by Steve and by Francisco. And again, you can find their contact in this slide. And so the part presented by Steve is about explainability in graph neural networks. So in short, so Steve will give all the details about that, but in short, the idea is that there is this feeling, and it's not only a feeling, there is this knowledge that neural network models are very powerful sometimes, but they are harder than other models to interpret. So it's harder than in other cases to understand why a neural network, a graph neural network, has taken some decision or some classification boundary is set in some way. Okay, and the idea of explainability, roughly speaking, is to try to get back something on that. So to try to understand what is the kind of pattern in the data that force the network to take some decision or to predict some outcome. Okay, and then the final session will be by Francesco, and it will be about heterogeneity. So essentially, how to extend these techniques. And again, Francesco will give all the details, so I will just give an idea of that. So heterogeneity is the idea of making a graph neural network able to work with data where nodes and edges in your graph have different types. Okay, so not just a uniform type of data, but a multiple type of data. Okay. Okay, so this is about the organization, and I would like to comment also on our choice on PyTorch Geometric as a library of choice. So actually, so what I'm going to present today is quite agnostic of any particular implementation. But on the other hand, for the practical session, we will need to show you some idea and some code in some actual language. And this library is very famous, very much used, and we like it a lot. So actually, all that we are going to present today and in the next time is based on this library. And one of the main reasons for us when we started looking at this kind of problem some years ago is that it's entirely based on PyTorch. PyTorch is one of the most famous deep learning libraries. And this PyTorch Geometric is built on top of this, okay? And in particular, it's very modular, and it integrates very nicely into the entire PyTorch infrastructure. So up to some detail that we're going to discuss. When you write code to train a graph neural network, the feeling will be exactly the one of writing just your neural network in PyTorch for any other type of data. Okay, so it's quite transparent to the user. When you understand some key concept, then we'll just forget that you're working with graphs, and you can write code that looks like you're writing code for any vectorial data structure. Okay, and so just a couple of words on this. So we don't have any kind of affiliation or interest in promoting the library, but if you're interested in using it, so they have an official GitHub repository, of course, and also an official page. And this library was first popularized by this paper, okay, now 4 years ago. So the library is quite recent. If you follow this link, you will find a lot of resources on the use of this library. There are also alternatives. So for example, one of the most famous one is this deep graph library. So we would like to mention that it exists because it's equally good. It's just that it's not our library of choice, but it's more a matter of taste. So if someone knows this library instead or want to use this one instead, every idea that you're going to present today will work equally nicely in that case, okay? And so apart from this tutorial, where we were aiming also at providing some theoretical insight or at least mathematical idea behind the definition of this kind of networks, of neural networks, there are also very, very, of course, complete and comprehensive resources to learn the use of the library. So if you go to this link that we are giving here, this is the official documentation of the library, and there are also very detailed installation instructions. So in particular, if some of you want to have a working version of the library to just run through the code that we will provide in the next session, I recommend to have a look at this link, and you can really find any detail for the installation. It's very, very simple, especially so if some of you has an experience in installing PyTorch, so if you're fine working without a GPU, the installation really takes a couple of minutes. If you need to have also a GPU, so running, that will require a bit more work, but nothing really incredible, okay? And in particular, on this page, they have a link to, okay, so the official resources, but also to external resources. So other people not related directly to the library who provided other kind of resources for learning the library. And this is the place where I should also advertise that we had in the past years with Antonio, so the presenter of the second session, we had also and with another guy named Giovanni Pellegrini, we had 2 online series for presenting details of the implementation and use of this library. Okay, so the tutorial that we are presenting today was somehow inspired by this series of tutorials that we ran 2 years ago now. Is a bit more now, but now, so you can also find some material here, okay? And also I would like to advertise that we are planning to have a third session of this online tutorial that will be run by the other two guys. So if you have a look at the page of Steve, you will be updated with any news in the upcoming month. So should they be able to set up another session of this tutorial, okay? And you are welcome to join if you're interested. Okay, so enough with advertisement, and now I will start actually with the content of the first tutorial of today. So for now, I will just start speaking about just the content of the session of today. So I would like to mention that I know that online seminars are a bit difficult, but if you like interrupting me at any time, I will be happy to answer to any question. Okay, and you can do it during my talk or also at the end or whatever you prefer. Okay. And okay, so the outline of what I'm going to present today is as follows. So first, I would like to give some motivation on the entire thing. So why are we interested in having machine learning and deep learning running on data which are defined by graph? Okay. Then for the definition of the next, of the actual inner working of this graph neural network, I will need to recall a couple of things about graph theory, but this will be really basic notions, okay? I'm not an expert in graph theory myself, and all we need for the following is just a couple of notions, okay? And then with this at hand, we can define the working of graph neural networks. So how are they different from any other fully connected neural network? And then I will present some computational aspects. So the situation here is similar to what happens with neural networks for vectorial or tensor data. So there is a general structure which is somehow shared by all neural networks. And then there are different layers which implement different ideas. So like in the vectorial case, you can have a convolutional layer or a fully connected layer, or name what you like. The same here. So there is a general structure that we discuss first, and then there are specific choices or ideas to end up with actual layer that one can implement. Okay. Okay, so this is the goal of the evening today, and let's start with motivation and applications. So there are actually plenty of use cases for graph neural networks, and broadly speaking, they find application in any case where one could be interested in running machine learning algorithms, so predictive or prediction or regression or classification algorithm on data which are modeled as graphs. So I'm going to tell you a couple of examples. So the first idea is anything that has to do with relational data. So you may think about biological or chemical structures where the nodes of your graphs may represent, for example, chemical elements, okay, like in this figure here. And then there are edges. So there are not only points which are with some property, but there are also edges. So your data set has an inherent structure where objects are connected. So the data is somehow relational, okay? And the edges in this example are just some chemical bonds between elements, okay? So your data set comes naturally in the form of nodes with properties and connection with properties. So it's a graph, okay? And an example use case of machine learning in this setting is, for example, to take a molecule, a given molecule, which is described again in terms of this graph, and try to classify some property of this molecule based on its structure. So I give you a molecule, I give you the structure, and you want to have a model that is able to take as input this molecule and output some property that this molecule has or has not, okay? This is an example of a graph classification or regression task, depending on the output, in the sense that the input is an entire graph and you want to assign a label or a numerical value to the entire graph, okay? So it's a graph learning task. Another example of great relevance in a lot of application, in industrial application, is the case of, again, on relational data. So you may think about the case where you want to model some behavior of some user. And in this case, you may think of an application where your nodes, so actually this is the case of a bipartite graph. So the nodes are divided into sets. One set is the set of nodes representing either users or, for example, products, okay? And the edges represent the user preferences. So this user is connected to some of these items because at some point in time it expressed a preference to one of these objects. Okay, so you have a graph where users are associated to certain products. And an example use case here may be the one of recommender system. So you may be interested in having a graph representing past transaction, and your goal is to predict if in the future an edge will appear between a user and a product that was not observed before. So in other words, you would like to predict if a user will be interested in getting one item. Okay, and this is an example of a task of edge prediction, in the sense that we want to predict the probability or the likelihood of having a new edge appearing between two nodes. Okay, so this is very relevant in commerce application, for example. And another field of use application of graph neural networks and machine learning on graph is in network science. So there are a lot of problems that are naturally described by graphs. So you may think about, for example, groups of interacting people. So the nodes are single person, and the edges represent some kind of interaction or contact between single users. Okay, this may be, for example, the interaction of member of a community or a network of people moving in a city and establishing some kind of interaction. And in this case, for example, a typical use case that was also of great relevance in the recent years is about epidemic modeling. So, for example, you may be interested in classifying a person's infection status based on the contact network. So you know the graph representing a person and its interaction in the past week, for example, and you may know that some of these nodes or people actually are got infected by a virus. And what you would like to do is to predict the probability that your node, so your person, got infected as well. Okay, this is a case of a node classification task. So the input is again a graph, but now the entity where you want to assign a label or a numerical value is a single node. Okay, and again, you want to make use of the entire graph structure. You are not just looking at individual vectorized information, but you want to make use of the entire topological structure of the graph. Okay, so these are applications in a lot of in three fields in science and engineering. There are also a lot of potential for application in computational sciences. So these are starting to be explored. So in the recent month, some papers were published about the use of these kind of techniques also in the case of computational sciences. And one of the reasons why graph neural network find a place also in this kind of field is that a lot of problems in computational sciences come in the form of graph. Okay, so examples are meshes. So if you solve a PDE by a finite element method, you know that at some point your domain will be discretized by a triangulation. Okay, and triangulation is of course a graph. So an example is in this picture, and this means that your domain is naturally represented as a graph. Okay, it's no more a continuous domain in the Euclidean space, but really it is a graph. And also there are cases of modeling of surfaces or manifolds, where again, if you have a dynamical system defined on a manifold, what is often done is to first discretize the manifold, and by that you obtain a geometric triangulated surface, and that again is a graph. Okay, and that means that a lot of data and data sets in computational sciences are naturally defined over a graph. So that this is really the natural data structure where some kind of problems are defined. And in this setting, there are a lot of typical use cases of machine learning. And I guess you are usually attending this series of seminars, so I'm not saying anything new. And but examples are, for example, in the case of direct or full solution of PDE or ODE methods. So for example, physics-informed neural network or deep operator nets, or a lot of deep learning methods that are specifically designed to solve a PDE or an ODE, but also in the building of kind of surrogates to approximate some kind of forward map related to a dynamical system of PDE. And example use cases are the acceleration of computation of Monte Carlo simulation, Monte Carlo estimates in an uncertainty quantification setting, or the solution of inverse problem, or the optimization of some parameters. Okay, so there are a lot of settings where machine learning models are currently used and are sometimes very, very competitive with traditional methods. Okay, and all of these are methods that are somehow naturally defined on data that come from graphs, as mentioned above. Okay, so there is a lot of space also in computational sciences for the use of graph neural networks to directly model this kind of data.
Hello.
Okay.
Yeah,
please.
Applications in scope here. I wonder, so graph neural networks are for graph inputs to a neural network, but they're not for graph valued functions, right? You can't use this. This is not a way to have output of a neural network that is a graph.
It depends what you mean. So you may have if you want really to output a graph. So there are two scenarios that you may, I would like to clarify what you mean. So you may have a function that returns you a value for every node of your graph. So that assign a vector of values for every node of your graph. That is perfectly fine.
I'm thinking of alternatives to language models for code generation.
Okay.
Is that in scope, or is it a different idea?
What again, sorry?
I'm thinking about as an alternative to language models for code generation purposes. Is that at all in scope for these kind of methods?
I'm not an expert of those methods at all. So, but there are methods designed to output a graph. So, but usually so that's more in the setting of graph generation, I guess. Or am I wrong? Or
yeah, graph generation. Yeah. But,
yeah.
So are we talking about methods is that part of what we can talk about?
Not directly here. So at the moment, the goal is most to work with inputs, which are graphs or, either entire graphs or nodes of a graph as inputs at the moment. Yeah, that's what I'm talking about mostly. Then there are adaptations of these techniques that are also able to output a graph, but those are not directly touched by what I'm going to discuss today. So.
Okay, thank you.
Yeah, thanks for the question.
Hi, Gabriel. Quickly, just one question. Could these type of methods also be used for manifold learning in terms of learning a low-dimensional manifold or some high-dimensional data?
Yeah, I mean, there are graph autoencoders, for example. So autoencoders that take as input a graph, so a function defined on a graph, and then there's some latent space, and then there's an output, which is the graph itself. So anything that can be done with plain neural network can be done here, essentially. So, yeah.
Okay, thanks.
Thank you.
I have also questions. Can we use also this method on knowledge graph? Since we know, like in knowledge graph, they usually, to apply machine learning, they use embeddings. They go from graphs to use scope function to manifolds, and they perform machine learning on numbers. But now you are saying like the input is a graph. Can we use this method directly to treat knowledge graph? Yeah, I guess so. Yeah, and the idea that we are going to see today. So all the idea behind these networks is that they learn an embedding along with. So the network is not just a neural network; it's also learning an embedding of the graph, essentially. So you can really, usually with traditional method, you start with a graph, you need some kind of vectorization technique to go with a vectorial embedding, and then you apply the other techniques there somehow. And instead here, everything is done in one pass somehow, okay? So it's optimized for your task. Yeah. Does this answer your question or? Oh, okay, thanks. Yeah, that's okay, more clear. Yeah, good. Okay, so thanks for the question. Thanks a lot. And so as you can see, there are a lot of cases where data are naturally defined on graphs. And so there are also very, very specific opportunities for GNN in this kind of, and especially talking about computational sciences, but these apply to any kind of data defined on a graph. So what GNN offer are a couple of really, really strong
plus, and one is topology awareness. What does it mean? That usually, if you want to apply plain neural network, this is what I was mentioning a couple of minutes ago. Usually, you need first to vectorize your data and then to do some process. So if you think about the usual way that data defined by the solution of a FEM model on a mesh like this is that you number your nodes and then you unroll your graph in a long vector, and that is your solution. Okay, but by doing that, usually you lose completely the topological structure. So of course you can have some metrics that represent the graph, but if you apply this kind of GNNs, you don't need to do that. So you just work with the graph structure. So you keep the node and edge structure of your data. And this makes a difference with traditional neural networks. So usually in that case, the data points, so what the input for your model is a variable, so a vector, and the output is whatever, so a number or a label. In this case, the data samples are just a couple of a graph and an output. So they can really define a function going from a domain of graphs to the given output. And there is also another and possibly even more powerful idea is that graph neural networks work, we will see, but what is called a neighboring aggregation idea. So they are local operations. So in particular, to provide some kind of representation or evaluation on the node, on the black node here on the right, all they will do is to look at the first order or second order or whatever order, but a neighborhood of the node. So the blue nodes here, and it will perform some aggregation operation on these blue nodes and provide the value of the function on this black node. So I will give details in the following, but this also at this intuitive level has some very powerful consequences. So the first one is scalability, because we can immediately work with very, very large graphs, because every time an operation is performed, is always performed locally. So we don't care if the graph has billions of nodes. We always need to look at single neighborhood, okay? And the second one, which is very powerful, and this is starting to be used also for multi-scale modeling, is the transferability across graph. So traditional graph processing technique are defined on the single graph, okay? Instead here, there is a possibility of performing what is called inductive learning. So what does this mean? Is that we really learn an operation that can be performed on any neighborhood, okay? So if I learn a model, I train a model on a given graph, and then I want to apply the model on another graph, which may, for example, represent another mesh or an adaptive mesh or a refined mesh, we can still apply the same model, because all it does is to look at neighborhood, okay? So it doesn't care about the global scale of the graph. So this is very powerful to be able to learn models across scales and over very potentially very large graphs. Okay. Okay, so this is a general idea and what are the promises of this kind of networks. And to define them, I will first go back and see some details of basic graph theory, or at least the couple of ideas that we will need in the following. So, so what is a graph? So a graph is a pair of two sets. One that we call V is a set of n nodes, so small n. So these are just elements, okay? And then we have a subset of the tensor product, which is a representation of a set of m, small m edges, okay? And there are either directed or undirected edges, so or graphs. So the undirected edges means graphs mean that anytime that there is an edge UV, there is also an edge VU. So this is what is depicted on the right. So we only care about the connection, and we are not caring about the direction of the connection. And on the other hand, the directed cases, which is the one with the arrow, means that there is no symmetry. So one node may be connected to the other, but not vice versa. Okay, so these are just the basic data structure. And then usually for a lot of interesting tasks, these graphs are not just this topological structure that is reported in the first block, but they are also given by some kind of feature structure. What does it mean? It means that we associate to each node a vector. So we call them X of V. So these are node features. So these are vectorial data attached to each single node or edge. Okay, so this is the depiction of a two-dimensional a graph with a two-dimensional node features on the left, and on the right, this is a case of a graph with a two-dimensional edge feature, okay? And we will represent them as matrices. So we just take the n nodes and we collect them. We stack the features in a matrix with n rows, one for any node, and let's call it dv, so the dimension of the vector for any node. Okay, an example of node features may be in the case of a mesh. You may think of having, for every node, you may think of having the 2 or 3 dimensional coordinate of the point. So you can also encode this information on the graph itself, and these will be a node features. On the other hand, you may have edge features, and in the case of a geometric graph, these may represent, for example, the distance between nodes. Okay, so one single number that gives you the distance. And also in this case, we collect features into matrices where the features are stacked in a row-wise structure. Okay, so a graph, just to summarize, is given by a topological structure given by nodes and edges, and by possibly some features on the nodes or on the edges. And we will see that graph neural networks are able to process also these features, not only the topological structure. And then there is some notion that we will use the following. So if we have a graph, there is this idea of the node neighborhood. So we call it N1. This is just the set of all nodes. N1 of V is the set of all nodes that are connected to the node, the center node. And similarly, we can define order K neighborhood. So this is just the set of nodes which are connected to the node V by a path of length K on the graph. Okay, so this is the idea of locality on a graph is given by this neighborhood. And then there are a number of matrices associated with a graph, and they provide a natural linear algebra representation of graph. So they work like that. So you first fix an arbitrary enumeration of your graph, of your nodes. So you have, instead of having a set, you give them a number. So now they are sorted. And once that is fixed, you can define the adjacency matrix, which is represented, for example, below here for the graph above. And this is just a matrix with the same dimension, a square matrix with the same dimension as the number of nodes in your graph. And it's a matrix which has a 1 if and only if there is a connection between node A and node J. Okay, so for example, the case here is for an undirected graph, so edges are symmetric, and this means that also the adjacency matrix is symmetric. So we are just plotting the upper half, and you see, for example, the node A is connected only to node F, and then on the row A, there is just a 1 between in position F. Okay, B is connected to 3 other nodes, and then there is a corresponding 1 in every one of these columns. Okay, so this is the adjacency matrix. Then there is the degree matrix, which is just the diagonal, which is a diagonal matrix, and every element of the diagonal is the degree of the node, so the number of connection of the nodes. Okay, this can also be obtained as the row sum of this matrix. So, for example, the node A has degree 1, and indeed, if you take the sum of the entries of this row, is 1, which is just the single connection that A has. Instead, if you look at the node A, which has degree 1, 2, 3, 4, if you sum this column, okay, there is 1 missing here. So what is missing? Yeah, because there is this 1 below. We're just looking, sorry, we're just looking at the upper part, so we need to look at this one as well. 1, 2, 3, 4. Okay, so it has degree 4. And then the Laplacian matrix, that so the name here doesn't say anything, but actually this represents a Laplacian structure on the graph. So this is connected with the usual idea of Laplacian, and it's really connected to all the kind of ideas that you can associate to a Laplacian in the Euclidean sense or on any manifold, but it's actually just defined by the difference between the degree matrix and the adjacency matrix. Okay. And altogether, this one, or if you look at it, for example, so these are fundamental matrices associated to a graph. And this will just provide, so if you look at the adjacency matrix, we could just have already defined a vectorized representation of a graph. Okay, so the topological structure is entirely encoded into the adjacency matrix. Okay, so in principle, the first thing that one would like to try is to just run first this kind of vectorization operation. Actually, is a matrix. So we transform our graph into a matrix, but still is a vectorial structure. And then you may be tempted to use any usual neural network technique of this matrix here. Okay, and indeed that can be done. So you can use any kind of neural network on this, but there are a number of limitations. So there may be computational ones, so there are a lot of zeros here, but that can be overcome by using sparse structures, okay? But there is one that is really fundamental and is really at the core of why graph neural networks are introduced and used. And everything is actually hidden in this first line, and it is that we really need an enumeration of our nodes to start with, okay? What does it mean? That actually, if we use this vectorized version of a graph to run our model, to define our model, everything is dependent on an arbitrary choice, okay, of the label that we are giving to the nodes. So this in detail means that given a graph, so topological, so a graph given by nodes and edges, we have multiple equivalent representation of the same graph. Okay, so every representation, so you have two of them here, and they are just the same graph where I decided another labeling or numbering of the nodes. Okay, and this representation in matrix form, so you see the corresponding adjacency metric on the right, matrix on the right, and you see that as soon as I change the numbering or the labeling of the nodes, the matrix changes. Okay. So for example, here the node A is connected to node F. So there is a 1 here. On the other hand, here the node A is connected to F and C. And this is reflected on the fact that the first row here has a 1 in position C and in position F. Okay. So once again, if I change the labeling of the nodes or the enumeration of the node, the vectorial representation is changed. Okay, so this is not a reliable way to represent a graph. So in particular, if I train any kind of machine learning model on my representation of the data, and then I give my model to you, and you want to test it on your data, you may have even the same identical data. But if you choose a different labeling of the nodes, you will end up with a model that is not even able to recognize the fact that two graphs are actually the same object. Okay, so we'll give completely nonsense prediction or outputs on the same data. Okay, and this indeed is a barrier to the application of plain neural networks. Okay, and indeed, in more formal terms, what we need here is a kind of representation or a layer which are either permutation invariant for graphs. So permutation invariant means that if I have a graph and I permute its nodes, and I'm trying to do some graph prediction task, I want the output to be unchanged. So as soon as I take the same graph, I want the output to be the same. So this would be invariant for permutation. On the other hand, if I have a node-related task, so for example, the classification of single nodes, I want a network which is permutation equivariant. So if I apply a permutation of the nodes, I want my output to be equally permuted. Okay, so I'm able to identify the fact that my node has changed its name, but the prediction is not changed in that point. Okay, so indeed, what graph neural networks will provide is a way to construct permutation invariant or permutation equivariant layers to be used within neural networks. Okay, if you have questions here, you can stop me. Otherwise, I can go on. Okay, let's proceed. Okay, so this is the general idea. And then I would like to tell you what is the idea of how they are actually defined. So the basic idea, I will first like to give you an overview, so a general idea, and then we will give into type of representation of this idea. But first, the general idea. So the idea is to learn a representation for a node based on the topological structure. So what does this mean? We start with a node, with a graph like this one, and we provide a label to the node, and we have some feature on the node in this case, okay? So we have an initial representation of the features, which we call d of 0, which has a certain dimension 0. And initially we take this as the features which are given for the graph, okay? And so they have dimension that we call d of v, so the dimension of the node features, okay? If the graph has no node features, usually what is done is to do some random assignment to features of the nodes, okay? So this is an iterative process where we start with some given or generated features for each node, okay? And then a GNN layer that we call f of w, so it's a transformation of this initial node graph into a new graph, and is parametric, so this w represented, there is a parametric learnable set of weights, and actually this will end up being a differentiable operation, okay? So a layer here is just something that takes as input the original graph and gives back another graph with the same nodes, but with updated node features, okay? So after this transformation, each node still has some features, but we call them x of 1, and they will have a given dimension d1. So the choice of this dimension is a parameter, is an hyperparameter of the model, okay? And one application of one layer is just taking the input graph with its own features and returning a new graph with updated features, okay? And so in general, it is like that, but this is made is realized with some key property. So the key properties of these function f of w, when applied to a single node, so the properties are two. So the first one is locality. So we want this function to be implemented, to be realized in a way that depends only on the single node where it is applied and on the neighborhood of the node of some order. Mostly in GNN, this is just k equal 1. So we are just looking at the single node and its first order neighborhood usually, okay? So the first property that we require to implement this function is locality. And the second one is invariance, which means that allowed functions here are ones that are invariant with respect to permutation of the neighborhood, okay? And also they are independent on the number of elements on the neighborhood, okay? So we will see concrete example, but what we will need to choose here are functions that work just on by looking at the first order neighborhood or small order neighborhood of one node, and such that they can be evaluated by operations that are invariant with respect to permutation of the node, okay? So if this is possible, we just have realized what we were looking at before. So we will just, if we are able to implement a function that has these two properties, we just got what we wanted. So we got a function which is local, so it can be scaled to very large graph possibly, and also that is invariant. So it doesn't care about the initial labeling of the graph, okay, or equivariant, okay. And once this is realized, so in the next slide, we will see how to actually define the function to obtain something like this. But if this is realized, so we will have a layer, okay? And now how is this used? So the idea is just to work like one does in any other kind of neural network application or architecture, like with plain fully connected layers. So the idea is to obtain a graph neural network by stacking multiple layers, okay? So in particular, we will have multiple transformations like the one that you see below, going from one graph to the other one, where at every iteration, so for every GNN layer, the features of the single node are updated, okay? And then by doing this, since this operation works by looking at neighborhood, the hope or the goal is that at the final layer, so let's say that we run a number of these aggregation and feature transformation operation, and we end up with this final graph with a final set of features on every node. And then the idea at this point is to forget about the graph topology. So we just throw away the graph and we just keep this list of features and we stack them in a column like this. So you see like the node A has features 2, 3, 1, and we put it here. Node B 1, 3, 1, and we put it here. So we have a vectorial representation of our graph, okay? And this vectorial representation, if we do everything properly, will be encoding two things. The first one is the initial set of features of the graph. And the second one is the topological structure, because every one of these feature vector is obtained by a repeated aggregation along over neighborhoods, okay? And that will mean that the numerical value within this, the final features, will also encode the topological structure of the graph, okay? And of course, one needs to see that this is successful, but the idea is that this should work nicely. And in any case, what we do is after application of multiple layers like this, we will have this vectorial representation that we call X of L. So L is the number of layers. And that this will just work as our node embeddings or marked features, okay? So this final vector is just the embedding that we learn for the graph, okay? So we can forget about the initial graph and we can just work with this set of this vectorial representation of the graph, okay? And then this can be sent as input to any machine learning or deep learning method. So usually this is the input of a final fully connected layer. So just a deep learning model that takes some metrics as input and a vectorial data set as input, okay? And in particular,
I have a question, please.
Please, yeah, go ahead.
Yeah, I wanted to ask, how did you assign the vectors on the label? Like A, you assign like 2, 3, 1. How did you do that?
Yeah, this is still unclear at the moment. So at the moment, I'm just assuming that there is a function that is able to take input features and return output features, okay? With the property that it should be local and invariant. Now, what I'm going to tell you in the next slide is how this actually performed, how this operation is performed, okay? Of course, the key of everything is how this is done, right? So if you just do it by random number generation, this will not work nicely. And I would like to go into the details in the next slide, yeah. But at the moment,
okay,
it's still listed. Yeah, thank you. Okay. But anyhow, when you have every one of these layers will be a parametric function, and we need a way to fix this parameter. And this is just done in a usual pipeline of a machine learning model. So what this means is that we stack all these layers one on the other. We end up with a
question as well.
You have a question? I don't hear.
So can you hear?
Yeah, please.
Sorry, just to continue previous one, apologies, I was trying to speak earlier and then the mic wasn't working. Can you just give an example on the previous slide or this one, like wherever you have this graph? Can you give an example of a real life graph that's like that and a transformation that would be done to it? Like what's a concrete real world graph that is on the screen?
Yeah, so for the transformation, I will like to ask you just to wait for 2 more minutes because I have plenty of slides about that. For an example of a graph, you may think about, let's say that you have a PDE and you solve it on a mesh. So the graph is representing the mesh. And the features is the value. So you have a two-dimensional field defined over your mesh, and these features are just the values of the field over the mesh. Or for example, even better. So you would like to solve a regression problem. So the input is your graph here, and you want to have and this graph is a mesh. So the connection represents the triangulation, and the numbers here are just the coordinates in the Euclidean space, the two-dimensional plane of the single nodes, okay? And then the output that you're trying to predict is the value of the field, of the solution field of one of the nodes, for example, okay? Or another example may be that you want to predict you have two classes of nodes, for example, infected or not infected, and you want to build a classifier that tells you if your node is infected or not. And these features may be describing any kind. So the connectivity pattern may be the actual connection that people had during a day, and the features may be any representation of the single person. So maybe age or some kind of comorbidity that may make it likely for a person to get a disease or things like that. Does it make sense to you? Or?
Yeah, no, thanks for the examples. It's still I'm struggling still to exactly, because I'm not up to date on the terminology, but it's always good to think of concrete examples when things get a bit
Yeah. So we will have other examples later. So maybe and in the next session. So hopefully that will be more clear in the future. Yeah. Yeah. So thanks for the question. But any one of the example that I presented at the beginning. So let's say that so this graph is in this graph the connection are the connection, and the features are, for example, an encoding of the type of molecule that is in every node. Okay, so the numbers will be an encoding of the single molecules, and that could be an example. In this case, the graph I think is clear, and the features of the nodes may be a descriptor of, I don't know, for the books maybe the price, the length, the type of book which is, and for the users could be the age, I don't know, any kind of characteristic of the person that would make it likely, that would be interesting for predicting its behavior. Okay, and in this case, yeah, and so on.
Can I quickly just continue that way? On that slide where you have the matrix representations, so previous, yes, because here the edges are now just simply whether there's a connection or not, right?
Yeah.
So this doesn't apply to any type of graph, right? This applies to just the types of graphs where edges are just there or not.
Yeah.
Where is it? Okay. And then when you talked about the fact that now if you relabel these, the matrix now looks different. So what is meant by relabeling here? You're not actually moving the vector representations. You're just changing the random label that you gave to it.
No, it's just that so the graph by itself is just defined by nodes and connection between nodes. But then to represent it as a matrix, I need to decide an order. So I need to decide that the first row here represent the connection of one of these nodes. And it's quite arbitrary to decide that here the first row is related to this label, to this node A, but it's just an arbitrary decision that this is the first node. I may, for example, assume that this node below is the first one, and that will make so the first row to look differently from here.
Yeah, but wouldn't you then? I mean, wouldn't you usually have like these labels on for the columns as well? So then below the columns would also just shift.
Yeah, exactly. So the first matrix is a permutation of the second matrix. Sure, it's obtained by row and column permutation. Yeah.
Okay. So where I was confused was when you were saying like if I develop a graph neural network and then give it to you to apply to your data. I mean, I just have to apply it correctly, right? I need to understand that in my case, the node E corresponds to the node A in your case, and then there is no problem, right?
Yeah, that will work nicely if we are just working on actually the same graph. In that case, we can. So that is somehow solving what is called it's kind of a graph isomorphism problem, which is quite computationally demanding, but still it can be done, right? So we can just identify the correct permutation that we applied. The point, and that is a complex but finite task. It is much more difficult when I train my model on a series of graphs, and I want the model to learn something about the graph. And then I want to test it on another graph that is not in my dataset, so I don't have a way to decide about the correct permutation, because there is not one that maps the new graph on one of the graphs that they have in my dataset. But still, I would like a model that learns something about the single graphs, okay? So it's not always the case that we are working on permutation of the same single graph.
Yeah, okay, yeah, thank you.
Yeah, thanks for the question again. Okay, so again, the way this is used is we stack all of them together. So every one of these will be a parametric and differentiable function. And then, but at the end, we will just a loss. So we will just have a data set given by inputs, so input graphs and value that we want to predict for the graph, or input graphs and value that we want to predict on the nodes. And then we can define a loss function pretty much as we do it for images or for other kind of vectorial data. And then based on that, we optimize the loss. We optimize the network, the parameter of the network based on the loss. And so the parameters of this, the parameter of this graph neural network will be automatically optimized based on a downstream task, okay? So this is why this graph neural network are able to learn in the same pipeline, both an encoding of the graph and a model that is able to solve the task. Okay, so they are not bounded to work on a predetermined or prescribed embedding of the graph, but they learn parameters that provide a good embedding for solving the single task at hand. Okay, so that is the same that happens if you run a convolutional network on images. Okay, so the features are learned along with the optimization of the method. Okay, so this is the way this kind of layer works. So they are just obtained by defining, and we will see how in the moment, function that take a graph and transform it to another graph by modifying its features locally. Okay, and in an invariant way. There is another small thing that I would like to mention, that sometimes when we do graph classification task, we don't want to end up like here with a vectorial representation of each single node, but we like to have a single vector that represents the entire graph. So if we are going to classify different graphs, we just want an embedding of the single graph. So in that setting, usually pooling is employed. And what is the idea is that you can aggregate the final. You can do two things: either aggregate the final node representation, so you take this final vector, which has one entry for every node, and then you do an aggregation of these. So, for example, you can take the average of these features, and you will call that your the embedding of your graph. Or you can also use pooling layers, which do the same as before, but what they do is that in an iteration they reduce the dimension of the node set. So they aggregate some node into, so they do the same as before, but the node of the new graph are just obtained by merging different nodes or a group of nodes on the previous graph. Okay, so you move from a graph with 6 nodes to a graph with 3 nodes, like here, and they do this automatically and they obtain a new features. Okay, we'll not go into the details of this, but just to mention that there are also ways to reduce the dimensionality of the graph in order to obtain a single embedding or feature representation of the graph. Okay. Okay, so this is a general idea, and what is missing is actually to define how these operations, so these single layers, are defined. So how to define an operation like this that takes as input a graph, gives as output another graph with modified node features, and in a way that the operation is local, so it depends only on low-order neighborhood, and in a way that is invariant. So we can permute the nodes and in the neighborhood, and the result doesn't change. So there are two ways of looking at the definition. One is from the point of view of really on the graph data structure, and is about message passing, and is what we will do now. And then next we will see how that is translated into linear algebra operation. So that can be written also in terms of really matrix vector operation. But first, let's see how it works in terms of this message passing operation. So what is the idea is that we can define a flow of operation, and this operation or computation work along the node structure. Okay, so let's see that we want to have the representation. So we have this initial graph, and we want to compute. We want to know what the layer will output when computed on this node here. Okay, so we want to compute, actually, let's see back here. We want to compute to see what it will be the representation of the node A after the application of the layer. So what we do is to look at the computational graph. So we see that the node is connected to the node F, okay, and this is the first order neighborhood of the node A, and this node itself. So if we do another jump, is connected to 3 nodes: B, E, and A itself. Okay, so this gives us a computational graph. So it's actually a natural structure to reach the node A staying on the graph. Okay, so the computation to obtain the representation of the node A will take into account that we can reach A only via F, and F, to reach F we can go through A, B, or E. Okay, so this is an unrolling of 2 steps of first order neighborhood of the graphs of the nodes. Okay. And so what we will need to look is just at the computational graph that gives us a way to reach A with 2 steps. Okay. And what is the idea is that every single layer will just be an operation involving this neighborhood. Okay, so to get to the representation of F at the next step, we'll just need to look at the representation of its first order neighborhood nodes at the previous steps. Okay, so what is represented here is the operation of a single layer of a GNN layer. Okay. And what is the idea? What are the operations that are performed here? So every one of these nodes has its own features on the previous iteration. And first, we perform a permutation invariant aggregation. Okay, for example, we can take a sum of the features, or the mean of the features, or the max of the features. And as you see, these are 3 operations that implement what we wanted, because they are invariant by permutation of, so they are commutative, right? So they are invariant by the reordering of these 3 nodes, and also the operation is independent of the number of nodes. So if I add 10 or 20 nodes here, this operation can still be performed. Okay, they have no parametric dependency on the number of nodes involved. So the first operation is to perform a permutation invariant aggregation of the features of the neighbor, and then we take this aggregation and we pass it through a learnable nonlinear mapping. Okay, so the actual learnable part of this mapping takes as input the invariant aggregation of the nodes, and is usually implemented in a way that is very much similar to what is done by a simple neural network. So we first apply an affine mapping, and then we apply a component-wise nonlinearity. Okay, so after the aggregation here, we will have just a single vector, so a single feature, and then we just take this vector feature, we apply an affine map, and then we apply a component-wise nonlinearity, so like a ReLU or whatever, so like one will do in a plain neural network. Okay. And and this is all. This is how GNN layer is implemented by these 2 ideas. Okay, and this kind of interpreting a layer usually is the one that is used in implementation, because it's very computationally convenient to represent it as a flow of operation along a graph. So Antonio will discuss about this in more details in the following. So just by showing the actual way that is implemented. And also it's fully parallelizable across the nodes, because as you see, I can work on this aggregation independently on each node, and I will just have an application of the layer on each node just by looking independently at each node in the graph. Okay. And also, if we do it layer-wise, we remove any kind of redundancy, because we don't need to recompute embedding. So every embedding is computed only once, and then layer by layer. Okay.
Sorry, I have a question.
Yeah.
On the previous slide. So in order to get, let's say, the feature for A, you need the feature for A. Isn't that some sort of a recurrent? How do you work with that?
So you start with the initial features that the node has because of what the graph represents. Okay. And you just propagate that to the next layer. And then at the next layer, the feature that you obtain from the previous layer, so like you start with the features that are given to the node, and if you don't have any, you can generate random numbers usually, and you just generate the next set of features for the nodes. And then you take these and you apply another layer, and it does the same to these features to generate the features of the new one. Okay?
Right, okay, I see.
Excellent question. Okay, this is from the point of view of message passing, but all this can also be, a comment that I forgot is also, this gives this way to represent, to understand these GNN layers also gives some insight on this, one of the bottleneck of this kind of method, which is about oversmoothing, which means essentially that since the information is propagated from one node to the other one, if you run too many layers, so if your network is too deep, the representation will more or less convert to a uniform node representation, because you are just propagating the same information over and over to all the nodes. So by the end, your node representation will it will likely be very similar between one node to the other. Okay, so actually this simple layer that we are going to discuss today usually have some kind of problem if you stack too many of them. And there are more recent techniques that try to address that issue, but just keep in mind that if you stack too many layers, you will end up with a representation that is too uniform to be able to distinguish different nodes. Okay. Okay, now let's try to see the same thing, but from the point of view of linear algebra. Okay. So we try to formalize this message passing in terms of matrix vector products. And what I'm going to show is just a prototype layer, and then I will show you real examples of layers. So this is how the layer works. So what does it mean? So this matrix here is the input node features. Okay, so it's a matrix with n rows, one for every node, and the dimension of the features. So we are at layer I. So the features that we currently have on the node are the one of the previous iteration, and the dimension of these is what we call d of the previous layer. Okay, so we start with this matrix encoding the features of the node at the previous layer. And what the layer will provide us is the new encoding of the features. Okay, so this is the output node features, which will still have the dimension of the number of nodes, but now with a new dimension that we prescribe. And this di and d minus 1 are design parameters, or are hyperparameters, okay, that we set for our network. And then there is a learnable set of weights. So this is a matrix that should be able to multiply our feature matrix. So it should have the dimension of the number of rows should be equal to the number of columns of our features. And the multiplication of these two will be the dimension, will have the number of columns that we have in the output. Okay, so actually up to here, we take the original features and we multiply by a learnable set of weights. Okay, and these represent the affine transformation. Here is linear. Okay, then there are other cases where this is affine. So first we do a transformation pretty much equal to what we will do in a plain neural network. So take the features and multiply them by a matrix of learnable parameters. And then there is the key to obtain equivariance, and is what really characterizes graph neural networks, and is that we multiply these features by the adjacency matrix, or by something that is related to the adjacency matrix. Okay, so this is an n matrix, so it can multiply this matrix, and what it does is exactly to implement this permutation equivariance, because as soon as we change the representation of the graph, this will change, and so we will take a permute version of the output. Okay, and then we can think, so this is just an example of a network. We may think about normalizing by the inverse degree matrix, and this will give independence of the degree, so on the number of elements in the neighborhood. Okay, and this operation in particular implements the local sum for every neighborhood, because if you take what you had before, so x times w, so this is just a transform set of features, and then you multiply by the adjacency matrix. So every row in the output features will just be obtained by multiplying one row. So you take one row of the adjacency matrix, and this will have zeros where there is no connection and ones where there is one. So these will just sum the features corresponding to the neighborhood of the node. Okay, so this implements the sum aggregation if you multiply specifically by the adjacency matrix. And then you multiply by the inverse degree matrix, so you are dividing by the number of elements in the neighborhood. So actually, this linear transformation within the parentheses actually implements the average of the previous features, each multiplied by a learnable weight. Okay, and then there is a component-wise nonlinearity, which just does what is done by nonlinearity in any neural network. So this just adds something that is not linear, and is a simple nonlinearity, so it's component-wise, so that it's easy to optimize. Okay, and so altogether, we first do a linear transformation of our input features, okay, by a learnable weight. Then we do a neighboring aggregation. So we aggregate the features by, in this case, by sum. So once again, we are doing a sum, and this implements the permutation invariance. And then we are doing a normalization by the degree. So once again, we are now invariant and also independent on the cardinality of the neighbor. Okay, and then altogether, when we apply the nonlinearity, we have entire GNN layer, which gives us the new embedding of the node, the new features of the node at the next iteration. Okay, so this is a way to write in terms of linear algebra the same operation that was plotted before in terms of message passing along the computational graph. And this other representation is useful because, I mean, this is usually not used in practical implementation because you need to have access to the full adjacency matrix and a number of computationally not convenience ways. So usually this is implemented in terms of message passing, but it's useful for layer analysis. And also it shows that if you actually perform all of these in terms of sparse operation, this is actually perfectly equivalent to message passing, in the sense that at every iteration, all operations are performed in exactly the same way as before, okay, as for message passing. And also this shows in a very convenient way that these kind of layers are easily transferable or over graphs, or actually that we are doing some form of inductive learning. Because if you look again at the layer here, you see that there is a part that is depending on the single graph, so on the topology of the graph and on the given features. But if you plug out this graph and you replace these three matrices by the one obtained by another graph G prime, which has its own degree matrix, its own adjacency matrix, and its own current features, you can exactly apply the same layer, provided you have a trained set of weights. You can apply the same layer and obtain the embedding for another graph, okay? And especially this weight matrix here, where this one is depending only on the dimension of the embedding that we have chosen as parameters of the model, okay? This is not depending on the number of graphs, of the number of nodes in the graphs, okay? So you can really train your model on one set of graphs, which has a number of dimensions, and then apply your model on another graph that has other number of nodes, because it's perfectly transferable just by replacing this block of matrices by the ones corresponding to another graph. Okay. Okay, that's it about the general structure of the message passing or GNN layers, and now I would like to end this first session by going through some main types of layers. So this, as I mentioned, was just a prototype layer, and this implements a local averaging, so local aggregation by averaging. But actually, there are a number of other ideas to define the layers that have exactly the same ideas, the same properties. Okay. And in particular, if you're interested in this kind of things, you can have a look at this page in the documentation of PyTorch Geometric, and it provides an entire classification of all the layers that are provided in this library. Oh, sorry, I need to connect my charger, but I will just start in the meantime. So, sorry. Okay, and the nice thing is of the way that these are implemented in the library is just they are defined as layers, or exactly the way that this is defined in PyTorch. Okay, so these are fully modular and composable. So you can take any one of these layers and you can stack them to obtain a deep architecture just by applying stacking different layers one on the other. Okay. So just give me a minute to connect my charger. So sorry. So what I'm going to show you now is just an example of these five, maybe the most commonly used layers. Okay, so this is like to say convolutional layers or recurrent layers or fully connected layers in the case of plain neural networks. But in this case, again, the selection of the aggregation operations give you the definition of the layers. Okay. And what I will show in the following is just the linear transformation. So I don't show you the nonlinearity, and usually you can add any kind of nonlinearity on these layers. Okay, so let's start. The first one is the graph convolutional network, which is also called GCN. And for every layer, I also provide the paper that introduced them. And in PyTorch Geometric is called GCN Conv, and this is actually very similar to what I showed you before. So is just obtained as before, but instead of multiplying by the inverse degree matrix, the layer is obtained by multiplying symmetrically by the square root of the degree matrix. Okay. Also here the notation is the one of PyTorch, so the weighting matrices are written as theta and those are W. Okay. And also when you see an at here, these are also self loop are added. Okay, but this here there is nothing to comment because this is just exactly the same layer that I defined before, just with this difference with the square root instead of one single multiplication.
So is this square root element wise?
This is a diagonal matrix, so yeah,
all right,
it's the same. It's a degree matrix, so it's diagonal, so it's the same thing. Yeah, yeah. But essentially, it's a very cheap operation. So, okay. Then this graph sample and aggregate, so SageConv, is performed in a slightly different way. So the aggregation is done in this way. So first, there is a weighting of the mean of the features of all the neighborhood, and then we add the single features of the center node with a known weight. Okay, this was introduced in another paper here. And yeah, again, here this can be written in terms of adjacency and degree matrix. And the key here is that there is a different weighting of the neighborhood and of the center node. Then another one is the graph attention network, which is very famously used. So it's an attention mechanism for the ones that know what this means. And the point here is that there is a different weighting of the single node and of the neighboring features. And there are these learnable attention parameters. Okay, so these are essentially weights on the edges and tell you. So they also learn an importance of the connection between the neighborhood. Okay, but again, the idea is again to take an aggregation of the neighborhood and an aggregation, so a global aggregation of the neighborhood, and then perform some nonlinearity operation. And these weights also are written in a way that make them learnable. So I don't want to give you the detail, but essentially they are designed in a way that make them learnable without being depending on the number of elements in the neighborhood. Okay, essentially you have some feature weight that you can learn, and this provides you the transferability across models, across graphs with different number of nodes. And the last one is the second to last is the Chebyshev spectral graph convolution. So this implements an approximation of the convolution operation based on the Laplacian of the graph, and it is discretized by some Chebyshev polynomial. So I don't want to give you all the details here, but the operation here is performed in a multi-level way. So the weighting of the features is obtained by starting by the initial features and then doing a number of weighting via some Chebyshev polynomial depending on the scaled and normalized Laplacian metrics. Okay, and this again provides you with a Chebyshev approximation of a spectral filter on the graph. And if you are interested in the details, these are very well described in the paper that introduced this idea. Okay. And then finally, there is this graph isomorphism network that was introduced more recently, and it implements another kind of transformation where, again, there is a weighting between the neighborhood and the center node, and then there is a learnable multi-layer perceptron that performs the nonlinearity operation on the learned features. Okay. So that's it for this session, and I would like to thank you for your attention. And do you have any questions? Or?
Yeah, thank you. Thank you very much. Yeah, I think there is a question on the chat. Feel free to.
Yes, can I open it in some way? I don't see it.
Yeah, I think she can just talk, Suresh. Or there's some. Yeah. Anyway, anyone who has a question, feel free to unmute. Yeah.
Chat. Now I see it. Oh, okay.
I think, yeah, just talk directly to Gabriel.
Hi, I might have a question. Can you hear me?
Yeah, sure.
Okay, perfect. Thanks for the nice talk. I'm wondering, do these graph neural networks really benefit from running them on a GPU? Because I have the feeling it's quite costly to connect the nodes basically and to check who has to be calculated. Of which nodes you have to calculate the average or whichever aggregation you are using.
Yeah, I see your point. So actually, I will likely to to defer the question to the next session, so that Antonio has a week to think about the answer. No, actually, I'm not an expert on that kind of thing, so I don't really know. So I know that in recent version of the library, they introduced a number of new implementation, full advantage of sparse operations, and that should work better on a GPU actually. But I don't know anything apart from this general hand-waving answer, in the sense that I don't know exactly how. So it depends, of course, on how you model your data set, right? And exactly at what level the GPU enter the loop. So actually, yeah.
Yeah, okay, then I will,
sorry for
I
that
will ask again next week and maybe we'll
thank
see.
you. So now Antonio knows what to.
Okay, thanks.
I actually have a question. Can you hear me?
Sure.
Okay, I'm not sure. Probably I was just lost at some point. But like the feature at like the first stage, how do we choose them? They are like randomly, or is like depending on like the model that we are trying to modeling, like on a practical way?
So if you have features, gives you. So if your data set has features, you should use those. Okay.
Mm-hmm.
So when the features represent something, you should use those, okay, because it's exactly your data. Even when you don't have them, for this kind of model to work, you need to have something to propagate across your graph, because still the propagation of the features and their aggregation gives you the learning of the topological structure. So usually, when you don't have any, you just generate random features or some constant features or something like that. But you need some kind of features. So if you don't have any, you need to generate them. Yeah, and usually they are randomly initialized, or there are some different ways to initialize them if you don't have any. Yeah.
Okay, thank you.
Thanks.
All right, other questions? All right, seems enough. Yeah, thank you again, Gabriele.
Thank you. And Boumediene, if I can, just 1 minute before concluding. Next time, Antonio will show some example with a graph obtained by the solution of a simple PDE, and I will just like to say one word. So we will implement it as a node regression problem, and it's just a very, very simple test case in model order reduction. So it's a thermal block. We are using it, we are producing with PyMore. So it's just a discretization of very simple PDE on the unit square, and is a model for heat distribution. And this is a parametric problem generated by having a parametric heat conductivity, okay? And this will just give, so the graph that we will see in the next week is just obtained by the mesh where the finite element solution is computed, okay? And in that case, the node features are just obtained by the concatenation of the position of the node, so the two-dimensional position, and then other values of the parameter and of the parameter of the heat conductivity generating the solution. Okay, but Antonio will provide more details on that. So thank you again.
All right,
hopefully see you next week.
Yeah, thank you. Bye-bye. Bye.
Bye.